Okay. There we go. Okay, so we're going to continue with more linear algebra material, and we're moving on to chapter 2, section 4, more multiplication of vectors. So let me bring up my OneNote. Sorry, it's just doesn't want to do it. Oh my god. Why, computer? Why are you making it so hard for me? Why? Okay, and my webcam is like way too big. There we go. Yay! Okay, cool. So let's do this. Oh, and I'm gonna highlight myself. Spotlight, I mean. Yes. Okay. Cool. So, we last time, yesterday, we were talking about vector multiplication. And I said that there were 3 different types. Okay, so the first one we learned about was scalar multiplication, which involves a scalar times a vector, which spits out a vector. And as a quick example, you can have like the scalar 5 times the vector 1 comma 2. It multiplies in component wise and you would get 5 comma 10. My zoom isn't right. There we go, that's what I want. Let's make this bigger. Oh, yes, full screen. There we go. Okay. And then we talked about another type of multiplication. We learned about the dot product, which is a vector times a vector, but what do you get out? So when you take two, so notice the scalar multiplication is a scalar times a vector and you get a vector. The dot product is a vector times a vector, but what was the type of the resulting thing? We got a scalar, good. And that was because, how does it work? Well, you would do something like vector 1 comma 2 dotted with vector 5 comma 10. And the dot product says, take the product of the components and add them together. So you get 1, 5 plus 2, 10, which is going to be equal to 5 plus 20, which gives you 25. Notice you get a number, you get a scalar. Okay, so vector times vector equals scalar. What do you think the next type of vector multiplication will give us? So we previously had vector times vector equals scalar. What should our third one do, which is called the cross product? It will be vector times vector, but what do you think we will get now? Yeah, good. And this is actually, historically, when they were like discovering, inventing all this, whatever word you want to use. Yeah, sharp and scroll. There was a lot of argument about this. So like the key players here were some people named Josiah, I think Willard Gibbs. He was at Princeton, I want to say. He invented vector calculus. It's like what we're studying. There was another man named William, I think his name was William Rowan Hamilton. Okay. And they came up with different ways to multiply vectors. I don't remember which one came up with which. I want to say that Hamilton came up with the cross product. And I want to say that Gibbs or someone else came up with the dot product. I could be wrong about that. But the fact is, there was like a lot of argument about like, well, how do you multiply vectors? And like, what's the proper way to do it? And what are the rules for doing it? And what's the relationship between them? And like, there's a lot of cool historical stuff. This was when they were inventing the study, what we're learning about now. Linear algebra was not like they hadn't like figured all the different pieces out like when it was an active research topic, basically. So actually, it's really cool because now like we learn about this like as undergraduates at some point about 150 or so years ago. It was what research mathematicians were like dedicating their careers to. So you should like, it's sort of crazy when you think about that in terms of like how much progress has been made. Like, you know, before it was like the smartest, most dedicated people who worked on mathematics were, you know, researching this, and now it's just something that people learn, you know, sometimes in high school or like, you know, first, second year of college, which is interesting, you know, like the amount of knowledge we've increased. Okay, so let's talk about the cross product. What is the cross product? So, how should I say this? So, first of all, to distinguish it between the dot product, so the dot product, we use a dot. So U dotted with V. The cross product, we put like an X, hence the name. So let's just start off with what symbols we use. Oops, I can't spell cross. Okay, so dot is dot product. The X is the cross product. Okay, the dot product gives you a scalar. The cross product is going to give you another vector. Okay, so there's something special about the vector that you get. So we call this the cross product. This is going to be some other vector. So what's interesting about it is that this new vector that you get, the vector U crossed with V, is perpendicular or orthogonal to both U and V. Okay, and the cross product only works with vectors in R3. Okay, the dot product, you can do it with vectors in R2. You can also do it with vectors in R3. The cross product is special. It only works for three-dimensional vectors. You can't take the cross product of two-dimensional vectors. Okay, dot product can be, you know, any sort of vector. Cross product has to be three-dimensional vectors. Okay, and perhaps you remember the right-hand rule? Do we remember what the right-hand rule said? I talked about this when we first started talking about vectors in R3. Like, what was the right-hand rule? curious. Do we remember what the right-hand rule tells us? Yay or nay? Yeah, line up your fingers. So you line up your fingers with the x-axis, you put your palm so it rotates towards the y-axis, and where your thumb is the z-axis. Yes, exactly. Cool. So people do remember. I feel like I'm doing my job. The right hand also applies here. The right-hand rule applies here. So let me draw a picture of what I mean. So because you're doing u crossed with v, you start with the u vector. So I'm going to like draw my u vector right here. So your hand would line up with u. And then your palm would be right here. And what you would do is you would rotate your palm towards the v vector. So the right-hand rule says you start with u, and you orient your hand so that your palm would face towards v. And whichever way your thumb points up, that's the direction in which u cross v will be. So your thumb is pointing up like this, so that's what u cross v will be in the direction of. Notice it's perpendicular to both of them. So you can imagine like u and v are in the xy plane, right? So this would be my u, this would be my v, and then u cross v goes up here with my thumbs. Okay, so like you can imagine, let me just say that again. You can imagine that u and v are in the xy plane. So your u cross v would be like up with the z-axis. It's perpendicular to both of them. Okay, does that make sense what I'm drawing? That's what I want to know. Okay, cool. Okay, so let's talk about like how you calculate this. So how do you know if two vectors are orthogonal? How do you know if two vectors are orthogonal? Question. Yeah, you could look at the angle formed between them. But how would you actually look at the angle formed between them? So like, we don't, assume we can't graph. So there's something we learned recently that would help you find the angle formed between them, a calculation that you could do. The formula for this even involves the cosine of theta, yes. There's a particular thing we learned about yesterday or the day before. There's a calculation that you could do that would allow you to figure out the angle between two vectors, which would help you. So there is something to do with the cosine, but if you don't know the angle and you only have the vectors, there's a calculation you could do to figure out if they are orthogonal. It has to do with that, yes. Okay, I'm gonna give it to you because I feel bad. You're like saying like everything around it. You could look at the dot product. If you have two vectors, U dotted with V will be 0 only if they're orthogonal. Why? Because remember, U dotted with V, like you guys were saying, is equal to the magnitude of U times the magnitude of V times the cosine of the angle between them. That's why I was like, oh my gosh, you're like saying like everything except for the fact that you would use the dot product to do this. Like you're talking about the angles, the magnitudes, the projections. I was like, oh my god, it's like almost there. Okay, so the cross product, U cross V. So what we want is U crossed with V to be orthogonal with U, which means if you take your cross product and dot it with U, you should get 0. And if you take your cross product and dot it with V, you should get 0. So I don't know how to calculate the cross product yet, but I know that given the fact that I want it to be orthogonal to U and V, if I dot my cross product with U and V, I should get 0. Does that make sense what I'm saying or no? I'm going to pause and wait for questions. Why did I write this here? Like this stuff. Well, yeah, but we don't care about the commutative property. I'm writing this down because it's the only way we're going to be able to verify that the cross product is orthogonal, right? The cross product, my cross product is orthogonal to U only if the dot product equals 0, right? So these are the conditions that I'm going to use to figure out what my cross product is. Does that make sense? Like this is my starting point. This is what I know I need to get. This is what I want to happen. And we're going to work backwards to figure out how to make this happen. That will show us how to calculate the cross product. Work backwards to figure out how to calculate the cross product. Okay, so the cross product, let's call it W. So W is going to be equal to U cross V, because I don't want to keep writing U cross V. And let's say that W has components W1, W2, and W3. Remember, because I said this only works for vectors in R3. So when I talk about W, I mean the cross product of U and V. And let's give some components to U and V. U will have components U1, U2, U3, and V will have components V1, V2, V3. Okay, so I can take these equations and rewrite them in component form. I know that the cross product, the dot product of W and U is 0. So let's write that. W dotted with U is 0, which is the same thing as saying W1 U1 plus W2 U2 plus W3 U3 equals 0. I also know that W dotted with V is 0, which means W1 V1 plus W2 V2 plus W3 V3 equals 0. And I'm going to copy this. Oops, that did not work. I'm going to copy this and paste it over here underneath this one. Oh my god, this is so cool. I love this. Okay, let's move it. Oh, shit. Okay, I want to move it. Oh my god. Why won't it let me move it? There we go. Okay. Oh my god, look, they like match up so well. Okay, so does it make sense? I just copied the one from the right and I put it right there. So if you notice, do you see how they share the V terms? Oh, wait. Oh yeah, sorry. They share the W terms, my bad. Right, this one's U. This one is V. So the top one is for U. The bottom one is for V. So what we're going to do is let's multiply the top equation by V3 and multiply the bottom equation by U3. Okay, so on the top you get W1 U1 V3 plus W2 U2 V3 plus W3 U3 V3 equals 0. Okay, then on the bottom, we're going to get W1 V1 U3 plus W2 V2 U3 plus W3 V3 U3 equals 0. Okay, hopefully the color coding shows really nicely what I did. What can you do now? Something really nice happened. So what can I do with these two equations? I'm gonna give you a moment to look at it. Normally when you're dealing with a set of two equations, you're trying to like eliminate stuff. So what can I eliminate? That's a better question. There's some stuff I can eliminate. Which term can be eliminated? Well, there's a lot of different V's. So, which particular term? There's 3 terms here. Well, there's more than 3 terms. There's actually more, but like this whole thing is a term. So which term can be eliminated at this point? All of these are constants. W1 is a number. U1 is a number. V3 is a number. Thank you. Yes. You look at these and you're like, oh, holy crap, they're the same. They both have W3, they both have V3, and they both have U3. So if I take the top and subtract the bottom, those disappear. So I'm going to take the top, subtract the bottom, and what I get as a result is now one equation with those two terms gone. I'm going to get W1 U1 V3 plus W2 U2 V3 minus, and then we'll do the bottom in a different color, W1 U3 V1. I'm changing the order now so it always goes WUV. And then minus W2 U3 V2. Okay, now if you look, this term and this term, what do they share in common that you could factor out? Yes. So I'm going to factor out a W1, and I am going to get U1 V3 minus U3 V1. And that's really interesting. Why is this interesting? There's like a symmetry here. What is the symmetry that we see? There's something really weird about, or interesting about those terms in the parentheses. Oh, I could hear someone talking, but it sounds like you're like at the bottom of a cave. Yeah, you have U1 in this term, and then you have V1 in this term. Here you have V3, and over here you have U3. So I'm assuming that's what you meant by opposite, right? Like the numbers change for the letter. Yeah, cool. Yes, that's exactly what I was hoping for. Okay, and now you look at this term, and this term, they share a W2 in common. And if you factor it out, you get U2 V3 minus U3 V2. And you're like, oh, holy shit, this is weird. Same thing is happening. U2 V3, U3 V2. So it's like, what the hell? Okay, and this is going to be equal to 0. Okay. Now, the only way for this to be equal to 0 is if W1 equals this stuff over here. And W2 equals not this stuff, but it's negative. Why does W2 have to be equal to the negative of that? It's a good question. Why does W1 equal the stuff in red, but W2 equals the negative of the stuff in green? Yeah, because it needs to be equal to 0, right? They need to add up to 0. Awesome. Okay, cool. Yes! I'm happy. Okay, so remember that W1, W is my cross product. And W1, W2, and W3 were its components. I now know the first two components of my cross product. And if you were to go back to our original equations above and substitute these things back in, you would find that the third component of my cross product would be... It's notice. Do you see how, like, remember we talked about how there's this symmetry? So actually, let's look at this. There's something really interesting that happens. This is the formula for W1. What number do you not see being used over here? Yes. And let's look at this. This is the formula for W2. What number do you see that is not used over here? Yeah. So if you look at the formula for W3, what are you not gonna see in it? Yes. Okay, cool. Now there's a formula, there's a way this goes. So, do you see how it's like W1, U2, V3? Actually, I'm just going to give it to you, but you can actually see that there's a pattern. So, do you see how it goes like 2, 3, and then 1, 3? So, we're going to start with U1, V2, and then it's going to be minus what? No. Because what happens if you have, let's look at the first one, U2 V3 minus U3 V2. What always happens with the letters and the numbers? Yes. Boom. And if you were to go and plug those back into the original equation, that's what you would get. But the fact is, it's like there's a nice way to remember this. So this is called the cross product. And there's a really cool way to write this. So the cross product of U and V is what's called the determinant. You put these things that look like absolute value signs of I, J, K, and then on the bottom you put U1, U2, U3, V1, V2, V3. Yes, it is. And we're about to see that we derived these matrix formulas by being crafty with our dot product. So the determinant of a 3x3 matrix, here what you would do is you'd start with I. And you would have the I vector times, now what you do is you cross this out. You forget about that row and that column. and then you just look at this stuff. And if you look, do you see how you have U2, U3, V2, and V3? Do we recognize that from here? So what you do is you multiply like this and subtract those two being multiplied. U2, V3 minus U3, V2. And then you get minus J. Now if you forget about this and this, do you see how you get these things? That's U1, V1, V3, V3, V3 and U3. Where do you see that? Right here. So you're going to multiply across and subtract. It's amazing. You get U1, V3 minus U3, V1. And then you do plus. You have your K. And then you're going to look at these two. You multiply across and subtract, and that's exactly what you got from up there. U1. Well, yeah, but okay, so I'm going to talk about exactly what the dealio is here. Okay, so I, J, and K, the I unit vector is which variable would you like to think of it as? The I unit vector is what axis? Right, so does it make sense that this is the x component, W1 is the x component, which is why they have the same formula. J is the y-axis. Notice that this is the same formula as that. K is the z-axis. Notice that that would be the third component. Whew! Okay, that was like a tour de force. We're gonna pause here and return to this tomorrow. And do some calculations. Okay, so we're just gonna stop right here.